Today's least squares regression. There are some formulas that are associated with this, and just a reminder that although you get to use your calculator and I show you calculator techniques, you can always use your white packet because those are the formulas that will be provided on the AP Stats exam for you. So if you always want to have those out with you, it might be helpful, and you'll see some of those today. So a regression line is one that's describing how a response variable y changes as our explanatory variable x is changing. We often use it to predict the values of y for some given set of x's. And we have this equation that's in this form, and we talked a little bit about yesterday, that y hat is talking about the prediction line. And a is the y-intercept and b is the slope. Extrapolation is something that we do a lot in statistics. It's the use of a regression line to predict way outside an interval some kind of response variable that's going to occur based on our explanatory variable. Now, it's great for oftentimes short distances, but for farther, maybe it's not so good. So for example, let's say I'm a shoe salesman, and I know that Air Forces are a very popular shoe brand. For 3 years, I record what's going on with the sales. And what I want to do is I want to minimize my wasted products. So I don't want overstock of 50 shoes, and I also don't want to be short by 20 shoes. So over the past 3 years, I record all that data, I make a line, and then I predict what I should do in the 4th year. So maybe that's good for the 4th year, but 20 years out, it might not be a good idea because maybe trends change. And so your regression line is only as good as the data that you have and how far out you're going to predict. Example, some data was collected on the weight of a white male laboratory rat for the first 25 weeks after birth. A scatter plot was produced for the weight in grams since the time in birth, which is in weeks, and shows a fair, strong, positive linear relationship. Remember the 3 phrases? So the strong, the positive meaning it's going up, and linear meaning that's the form of the graph, which is 99% of the things we talk about in here. And the linear regression equation is modeling this data fairly well. So this is the equation that we're going to use. As we look at this equation, this y hat equation, our prediction, our least squares regression line equation, the slope of the regression line in this case is going to be 40 because that's the number in front of the x. So the slope is equal to 40. Bless you. What does this mean? It means the rat gains 40, was it grams? Grams per week. What's the y-intercept? The y-intercept is obviously the other thing, so the y-intercept is 100. What does this mean? It means the rat weighed 100 grams at birth, or at time 0. And if we wanted to predict what the rat's weight would be 16 weeks later, what we would do is we would say that our prediction is going to be the 100 plus the 40 times 16 weeks, because that's the x, or the explanatory variable. And you type that in, and I think, based on my sources, I get 740 grams. If we use this model, and remember we were just talking about how far out maybe it's not such a good idea, and we use this to predict 2 years later, that means that my y hat would be 100 plus 40 times the number of weeks 2 years later would be, which 104 weeks later, or in other words, 4,260 grams. Now maybe that doesn't mean so much to you, but my sources tell me that this is about
10 pounds.
close, yeah, 9.38 pounds, based on the information that they give us here about the conversion that 1 pound is 450 grams. And as you think about that, a rat weighing 9 pounds, like I have a cat at home, my cat weighs just under 10 pounds. So to have a rat that big is unlikely. So I guess I would say, in this particular instance, it does not seem likely that a rat could weigh this much.
There are some rats in like the sewers.
Yep, and there are pink elephants. Yep. All right, residuals. Residuals sometimes are also known as the error, or how far off is your prediction from the actual value. So here are some examples of residuals right here. Here's a residual, here's a residual, there's a residual, here's a residual, everywhere residual. Old MacDonald drew a residual. So residuals, when you look at them, are your actual or observed values minus your predicted values. And what happens is they tell you how far you're off. So you look at whatever the actual data point was, that's usually provided in a table, you subtract off whatever your y-hat or prediction regression line gave you, and that's your residual. So here is an example of what's going on. You see the data point, and then down to the line, which is your prediction line, where that would have been the vertical distance, that's called your residual. A least squares regression line is assuming that the sum of the squares of your residuals, and you'll see a picture later of what that means, is as small as possible. And the cool thing about your calculators is they calculate that for you. A long time ago in a faraway planet, we had to do that by hand. It was a major pain. Now you don't really have to do that anymore. Down below here, we see some formulas that are associated with that. So we have our former equation, this prediction line, least squares regression line thing, the y-hat, and they talk about how to get these things from your calculator based on some information. So sometimes they don't always give you all the data that you need, and you're going to have to use that information in order to get it. So first of all, you see that you have the slope here, the b, and what you need to know is that you calculate this b right here by using this formula. So the r is standing for your correlation coefficient. The sy is talking about the standard deviation of your y values, which you're going to be putting probably in list number 2. So it's the standard deviation, or what you'll see as sx, even though it's the y variable, in list 2. Sx then is your standard deviation in list 1, or of the x variable, the explanatory variable, whereas the y was the response variable. And so that's how you find the b. And then the a similarly is found with data that you have from those two lists as well. This a for your prediction line is whatever the mean is from list number 2, which is y bar, minus what you just found as the slope in the orange circle, times the mean of your x list, which is list 1. And we'll do an example of that in just a little bit. I'm going to put all these different things on here. So r, that's the correlation. Sy is the standard deviation of list number 2, otherwise known as your y list. Sx is the standard deviation of list 1, otherwise known as your explanatory or your x list. The y bar is the mean of list number 2, and the x bar is the mean of list 1, and the b, we just got done talking about how to find that. That's the slope based on your correlation times the standard deviation of your y over the standard deviation of your x. So down below here is a picture explaining how the least squares works based on our previous diagram. And so what you'll see is we had our residuals, and then based on the residuals, they just draw a square. And they're saying that this space, when you add all that up, is the smallest possible. Now, you're not really going to be using that on the AP exam or on our exams as far as like a test question, but they're just trying to explain why they get it and why it's used. All right, on our next slide,